Okay, so our next speaker is Arghya, and he will speak about online iterated bipartite.
Hi. Thank you all for inviting me here. Please feel free to ask questions at any point. So over the last year, I have been working on matching related problems. Matching is a central problem in online algorithms, and it has several applications like matching organ donors to patients or matching online advertisements to search queries. So, and recently there has been some results regarding this, and I'll be presenting those results. So first of all, notice that both the examples that I have mentioned have this bipartite nature: organ donors, patients, or online search queries and advertisements. So I'll first define what bipartite matching is. So imagine a bipartite graph and it has some edges, and the matching is basically a collection of these edges such that any vertex is incident on at most one such edge. So the red edges here are for the matching. And our goal would be throughout the top to find the maximum sized matchings. So this is bipartite matching. Let's now try to understand what is online bipartite matching. It's basically the online version of the problem. So in online bipartite matching, one partition will be offline. Throughout this talk, we will assume that the left partition would be offline and the right partition would be online, as in it arrives one vertex at a time. And as a vertex arrives, we would have to select one edge from its neighborhood to be matched. So when the first vertex arrives, we have two choices, either the top edge or the bottom edge, and we could have matched to any of them. Now notice that the adversary will provide the next vertex and the next edge, but he may adapt to our choice and he may provide the next edge in such a manner that we cannot improve our matching further. In this case, we would have a matching of size 1, whereas the optimal matching would be size 2 in both cases. So what we have seen now is that if the adversary adapts, we cannot do better than half of the optimum size matching. So we will look at a different adversary now, an oblivious adversary. An oblivious adversary is an adversary which decides the graph beforehand, and it does not change the choice of the graph depending on our point process. So imagine the following: the adversary has determined this graph, but we will receive this graph one vertex at a time. So when the first vertex arrives, it has edges to v1 and v2, and the next vertex will have an edge to v2, but we as an algorithm, we don't know that. And one potential algorithm may be to match with v1 or v2 each with half probability. And if we happen to match to v1, then we would be able to match to v2 on the next edge. Otherwise, we would have a matching of size 1. So with half probability, we would have a matching of size 1, and with half, we would have a matching of size 2, resulting in an expected matching of size 1.5, whereas the optimum matching is of size 2, and we cannot do better in this case. So what have we seen till now? We have seen that if the adversary adapts, we cannot do better than half, and if the adversary is oblivious, even then we cannot do better than 3/4. This is the previous example. However, Karp, so 3/4 is not optimal, and Karp, Vazirani showed in 1990 that no online algorithm may attain the ratio better than 1 - 1 over e. And they also provided an algorithm which matches the same, as in it provides a matching of the same ratio in expectation. So we will just spend 1 minute on what this ranking algorithm is. The ranking algorithm is the following. It takes all the offline vertices and it shuffles them uniformly at random. So one of the vertices may go to the top, another vertex goes to the second, and so on. So it induces a ranking in the vertices. And now, at any point, let's say we have some edges which are matched, like some vertices which are matched using some edges, and an online vertex arrives. What the algorithm does is, it would look at the neighborhood, and it would look at the topmost vertex, which is unmatched. And it would basically match it to that. Topmost in the sense of the ranking that we did. However, this algorithm only works for unweighted edges. So next we will define edge-weighted bipartite matching, and we will see what goes wrong when there are edges.
So this ranking algorithm works with this ratio 1 - 1 over.
1 over, yeah.
Okay, so there is a matching upper.
This problem is completely solved. So now we will be looking at edge weights. So when there are edge weights, so let us look at the following. So one vertex arrives and it has an edge weight of 1 to an offline vertex. And we ask, do we match it or do we match this edge or do we not? If we choose not to do a matching, then the optimum matching is of size 1. However, we are left with a matching of size 0, which is infinitely worse. On the other hand, if we decide to match this edge, then maybe on the next vertex, another edge appears, and it has a very high edge weight, W. And now this vertex is gone and we cannot use the same vertex for matching again. So it can be made into a formal argument and shown that we cannot attain any non-trivial bound for this. So we will change this model slightly. We will discuss what a free disposal model is. So let's take a look.
The unweighted setting, you have these nodes coming in on the other side, and you measure and you compare optimality to what the people have done. You measure optimality when all the nodes have come, where every time.
Exactly, after every node has come.
After every node.
But on the other hand, we could also have considered a smaller sized input where there are maybe 10 vertices and compared to that. But we will always compare when everything has come. The graph is decided before that.
Yes, you could stop the input.
You are not allowed to stop the input.
And it will be 1 and it will have that ratio with whatever the
That's true.
The person who has foresight to this one, it will compare it always to the person who has seen the thing up to this point and done this. You're always comparing it against them.
Yeah, so the oblivious adversary just means that you are not allowed to stop the graph midway.
Same thing is happening now on your weighted set.
Exactly. Yeah. So what we just saw is that having edge weights is a bit troublesome. So we will give some special power to our algorithms. We will discuss what a predisposal model is. So imagine an online vertex U1 arriving and it has these two edges, one of edge weight half and another of edge weight 1. And we decide to be greedy and do the matching with edge weight 1. Now again the same thing may happen. Another vertex appears and it has a very high edge weight W and we cannot match. But our free disposal model allows us to dispose of this matching, which we did. Thus, it will free up this vertex V1 and it will allow V1 to now get matched to W. However, since we decided to match U1 to V1, we would not be allowed to match U1 again. So what we will be finally left with is this following matching. We disposed of the previously matched edge and we did the current matching, but we are not allowed to match U1. That decision was final. So we are left with a matching of size W, whereas an optimal matching would have been of size W plus half. Fair enough. It's a section. It's a section.
It's a section. It's not like
Recent breakthroughs. Yeah, so there have been some recent breakthroughs and I will describe them now. On the right hand side, this ratio would be the ratio. On the left hand side, there would be algorithms, and on the right hand side would be the expected size of the matching divided by the size of the optimal matching, also known as the completive ratio. Yeah. So it can be shown that a greedy algorithm attains half in this aggregate setting with free disposal. Then fairly recently, Farbach, Tuam, Tao, and Zarimogakam showed that you can attain a completive ratio of 0.5086. They used a novel concept called OCS, which I'll describe shortly. After that, there has been a result by Shin and Ann, who improved the notion of OCS and obtained 0.5093. And then there has been a result by Blank and Charikar, who obtained 0.5368 by again improving this concept.
Sorry, what are the numbers? Are the numbers?
Yes, so the left-hand side, these papers provide an algorithm.
No, I'm asking, do these numbers on the right-hand side appear naturally in some array or
No. They're if it runs some numerical program and output of linear.
Okay.
These are not the right numbers. You can
How far are these numbers from this 1 minus 1 over?
Exactly, that is the next slide. So, so these are the best known lower bounds, and the upper bound till now it is still at 1 minus 1 over d, the best known upper bound for the unweighted setting. And as we can see, there is still some gap. Okay, so now, like I mentioned, that all of them use something called an OCS, and I'll now be describing what an OCS is. Any questions so far? So for the next few slides, let's ignore what matching is and everything. We will describe a completely different problem. So OCS involved, like there would be a sequence of elements arriving one after another, and each element would be a pair from a given set. So let's say that the set is the set of all alphabets, just for simplicity, and pairs of alphabets would arrive one after another. And whenever a pair arrives, we have to select one among them. Let's say AC arrives and we decided to select C. DB arrived and we decided to select D, and so on. Pair arrives, we select an element. Pair arrives, we select an element. So we could have, of course, tossed a coin and did that. However, what we want to do is something more. We want to say that if an element appears multiple times, we want to increase its chances of being selected. So notice that A appeared, let's say, twice. We want to increase the chances of A being selected. B also appeared multiple times. Let's just define this concept a bit more formally. So we will define what is called a gamma OCS. So let us assume first that we decided to flip a coin and select elements at every step. Then if an element appears k times, the probability that it is not selected at the end of k times is 1 by 2 to the power k. Does that make sense? Sorry? In total, like as in you look at how many offline dimensions.
So this OCS is some property of algorithms and it can be implemented.
Exactly. Exactly.
In many ways.
At every stage, you should have this problem. K. You have seen the stream, no time. No time. If you have seen the stream so far and you've seen it,
No. The complicated, not smart.
okay, the way he's going to define, he's going to define me what we are, in general, we have to do it by identity. No, time is
Yeah, this is the entire. Yeah. So once again, if we decided to toss a coin at every time, and if an element appeared in k pairs, then the probability of it not being selected is 1 by 2 to the power k, the very first quantity. However, what we are saying is that the probability of it not being selected is not only smaller than 2 to the power k, it is also smaller by some, like it's smaller than 1 by 2 to the power k times 1 minus gamma whole to the power k minus.
So
It's even smaller.
if we set the gamma to be 0, we can choose.
That is the next slide. Let's just put it the gammas and so, as Pavel said, gamma equal to 0 means picking independently. And what gamma equal to 1 means, so if you put gamma equal to 1 and k is larger than 2, then this quantity becomes 0 and hence the entire probability becomes 0. So gamma equal to 1 means if an element appears twice, you have to be selected. It can be shown that such a gamma is not possible. One can see that just from the first 3 terms. Let's leave that as of now. So it can be shown that gamma equal to 1 is not possible. So just a disclaimer slide that what I defined is a weak version of OCS, and the paper actually needs a stronger definition of OCS. We will not go into that, but whatever I will show for this presentation actually goes through with the stronger definition. So there's the stronger definition of OCS. Okay. So we started with matchings and we defined OCS. How are they connected? So there is a theorem by Blank and Chakraborty. They show that if we happen to have a gamma OCS, then we have an algorithm which solves online age-weighted bipartite matching, and it attains a competitive ratio of the following. Now, once again, let's just see what the different gammas would give us. So a gamma equal to 0, we know we can attain gamma equal to 0 because that is equivalent to picking uniform independently. Gamma equal to 0 would basically give us half, nothing better than greedy. Whereas on the other hand, a gamma equal to 1, we know that it is not possible, but still, if we had a gamma equal to 1, that would give us 5 by 9, something beating half. But still 5 by 9 is less than 1 minus 1 over e. Now, notice that any non-trivial gamma, any gamma other than 0, would allow us to beat half. So now, throughout the rest of the talk, I'll just show that there exists a gamma which is non-zero. And yeah, so we will show.
What is the max?
What is the max?
This actually, you know the max. I mean, so 3 plus 2. I mean, this is
5.
It's 5 by 9.
Yeah, I wrote 5 by 9.
No. I mean, it's a non-linear.
Yeah, but any gamma other than 0 would give you something better than that.
So,
Just give us 2 ways.
so basically, with this algorithm, you can't do better than 5 by 9. So basically,
Exactly.
you can't reach 1 minus 10 by 9.
Exactly. And it would give something better than half because 2 by 3 is better than half. They correspond to vertices of a bipartite.
Pairs.
Yes. So at any point, you would have 2 vertices and we want to select which of them we want to match to. And the way we want to match is we will use the vertices.
So this fraction is increasing with gamma.
This fraction is?
It's increasing with gamma.
Yeah.
So what person? You say upper bound unlimited case, please.
So in the unweighted case, you don't want to do free disposal because you have already matched something. You dispose of that matching. Yeah.
Even if we get a 1, you get a 1. Huh? Even if you dispose, just get a 1.
Yeah, there's no point in disposing that way.
Yeah, so the comparative ratio is 1 minus 1. Okay. Yeah, so with the next slide, I'll show that this gamma OCS is not something imaginary and a 1 by 16 OCS exists. So once again, pairs are arriving and we are selecting elements. And let's say, I'll now describe an algorithm to pick this element. So let's say an element appears, let's say G comma F. What the algorithm would do is it would try to first draw some nodes to this element to either a past node or a future node. Let's try to do that. So we will toss a coin, and depending on the coin toss, we would draw a link from the current node to either a past node or a future node. So if it's heads, we draw links to the past nodes, and if it's tails, to the future nodes. The future nodes have not yet arrived, but we will draw the link in anticipation. The moment the future node arrives, we will find it. I think you're asking that question, and I think we can attain gamma equal to 1, but I'll not like to make a bigger.
This is very straightforward.
Yeah.
So this definition, I think you can. The stronger definition, I don't know. This definition is what the
Yeah.
we saw.
This is tricky.
No, it's tricky.
Say somebody not selecting something.
All of the correlations, yeah, it's not all.
In the weak definition, you can strong definition.
The definition they have not put up, which is not strong enough for the actual thing, I think you can get confident in the offline setting, which is also not more feasible.
So the connection that you're going to put to the past node, are you putting it to specific?
Okay. So now I'll describe which nodes I'll put a connection to. So if it's a heads, I'll connect it to the past appearance of the first element or the last occurrence of the first element or the last occurrence of the second element. That is the last occurrence of D or the last occurrence of F. And if it's a tails, I would draw links to the future occurrence the next consecutive, like the next future occurrence of the first element or the future occurrence of the second element. And the way to decide which of these two I would do is I would again toss a coin, and if it is heads, I'll do it with the first element. If it is tails, I will do it with the second element.
So for the future connections, you already decided that I'm waiting for the next occurrence of
Yes.
correct. Okay.
And the moment it arrives, I'll drop it.
This point of the pair.
Yeah. So I have 4 choices: past occurrence first element, past occurrence second element, future occurrence first element, future occurrence second element. So 2-point process to decide among these 4 choices. Yeah. So this is how the algorithm would do. On arrival of a node, the first thing we would do is we would toss this coin to decide which of these links to draw. Now it might so happen that the arrival of the node completed a link from a past node, and I also tossed my coin and I happen to link back. These links would be what I would call a double link. And whenever a double link occurs, it would be with respect to some element. Because whenever a link occurs, it happens with respect to some element. So whenever a double link occurs, there is a common element in between those two. So whenever such a double link would occur, I would pick deterministically. Whatever I have picked in the past turn, I would pick the opposite. So for instance, now when there is a double link, I would basically go and ask, what did I pick here? If I happen to pick a, I would not pick A now, I would pick a B. If I happen to not pick A, then now I would for certain pick A. So this is what I would do in case if it's a double link, and if it is not a double link, I would just arbitrarily pick one of them. This is my algorithm.
Sorry. So the first thing was A comma C. And A comma C had a double link with A comma B.
A comma C created a link to a future A. So I
And
get
then A comma B we had a
double link.
so there is
So now when A comma B arrives, I'll go and ask, what did I do when A comma C was there? Did I pick A or did I pick C? If I picked C, I will pick A now. And if I picked A, I will pick B now. So this ensures that whenever there's a double link, I have picked A for certain. Exactly once, but for certain. So now let us try to analyze this. So let us assume that an element A appears k times in total. And we will try to evaluate the probability that A is not selected even once. So when can it be the case that A is not selected even once? Then like if A is not selected even once, then it must be the case that these nodes did not get doubly linked. Even this did not get doubly linked. Like none of them got consecutively doubly linked. Let us take any two consecutive, and let us ask what is the probability that it did not get doubly linked. Like these two did not get doubly linked. So with 1/4 probability, he would have linked to the next one, and with 1/4 probability, he would have linked here. So with 1/16 probability, they would have linked to each other. So the probability that one such pair did not get doubly linked is 1/16. 1 minus 1/16. And since A has appeared k times, there are k such choices to be doubly linked. K minus 1 such choices to be doubly linked. And I would have liked to say that, oh, these are independent k minus 1 choices, and hence this is 1 minus 1/16 to be k minus 1. But these are not independent. However, what is true is that they are negatively associated. So if the second time that A appears, this node, if it is not doubly linked to this node, it only increases my chances of being doubly linked to the next node. So this negative association still allows me to write this inequality. So in order for K to not be selected, this double link should not occur. But not only that, even in one of those nodes, I should not have picked A, so this should happen with probability 1/2 to the power k. I'm almost done. Yeah. So now combining both of them, the probability that A is not selected should be 1/2 to the power k. 1 minus gamma to the k minus 1. This is gamma OCS for gamma equal to 1/16. That is.
If you put 1/16 in that equation, sorry,
Yeah.
not equation, that formula, what
You would get 0.505005, which is worse than what all of them
The
got.
first step.
Next. Yes. Yeah, I just wanted to compare in the chart. Yeah, yes. So it is like it is even worse than this, but we beat half, like which is something which we were not expecting.
So this easy trivial algorithm. I mean, not trivial, but
Yeah, okay. Thank you. Yeah.
So thank you for listening. Other questions?
Yeah, so is there a, like, how far can this technique be pushed to the, is there an obvious bottleneck as to,
Is there a bound for gamma?
yeah,
So the currently known best bound for gamma is 1/4.
for OCS or for the
For the actually stronger version of OCS, I think.
not quite. These definitions are strong.
Is there a better construction node than Monday?
possibly
Sorry.
No, in the offline.
Is the construction node better than 1/16?
Okay, those algorithms exactly, okay, they go by OCS.
No,
They just improve the.
the second one is
The last one is to.
So you have to comment, what's the, why is the also better than 5 lines?
The first one. Yeah, the first one,
Yeah,
in the first one, they gave an OCS better than 1/16. That's also a weird number, I don't recall the number. The second one, they did not use a two-way OCS, they do a three-way OCS. It means not select from a pair, select from a three level. The last one is a bit more fancy, a multi-way OCS. I'll understand. Yeah, I think I'm out of it. Any more questions?
This indicate what is the interesting puzzles, put the reading cap and reading cap. The ideal cap on the white is black. I think we're going to look at it because you can mark. At least one of us have to get their own color palette. The puzzle is very simple. Interesting puzzle.
Yeah.
But we can put anything for that how many of them get it right.
Yeah, but it's funny, this problem is the more general sense, the young version, we don't know the right answers. It's a very key problem. If you program it, you just want to ensure that if anything of this right, it is selected. Yeah, so then you are just saying, and you can simply assume that nothing of yours.
You should get the marginal correct half.
So the stronger version of it. You should get the marginal for every guy.
Also, like, the first time also there should be.
Yeah.
Absolutely.
You do this way of sampling, right, so that the marginal for every guy is exactly half.
And yes,
Okay. Okay, so let's send speaker.
Thank you.